Hello, this is Mrs. Sargent, and we are going to be talking about the ideal gas law today. The ideal gas law combines the first three gas laws. So the other day we talked about Boyle's law, Charles's law, and Avogadro's law. And each of these three laws had a constant in them before we did some rearranging. What the ideal gas law does is it combines all three of the constants into one constant that is called R. So the ideal gas law combining the first three gas laws gives us V equals R times T times N divided by P, where R is known as the universal gas constant, and the value for R is 0.08206 liters times atmospheres divided by moles times Kelvin. All of this is the unit for R. And what R does is it allows us to cancel out units for some of our other variables. Today we're just going to focus on this R value, and we are going to not worry about calculating any other R values today. So to get everything up on the same level in the equation, we get P times V equals N times R times T. Where P is our pressure, and we have to be a little bit specific about some of our units in the ideal gas law because of our universal gas constant. The unit of pressure found here is atmospheres, so we need our pressure to be in atmospheres. V is for volume, and again we're going to take a look at our universal gas constant, and liters is the unit for volume. N is the number of moles. Then R is the gas constant. And then T is the temperature, but it has to be in Kelvin. Just like we looked at the other gas laws, all of your gas laws, the temperature has to be in Kelvin. So if we're given degrees Celsius, we're going to add 273 to get our Kelvin temperature. So the ideal gas law is based on experimental measurements, and since they're experimental measurements, only ideal gases obey this equation. It works well for real gases if they are at a low pressure and high temperatures. But for our purposes, we are going to assume that all gases are ideal unless you're told otherwise. So we're going to take a look at 3 different examples for the ideal gas law. This first problem says a sample of hydrogen gas has a volume of 8.56 liters at a temperature of 0 degrees Celsius and a pressure of 1.5 atmospheres. Calculate the number of moles of hydrogen present in this sample. So the information that we're given is 8.56 liters, 0 degrees Celsius, and 1.5 atm. So remember, the ideal gas law equation is PV equals nRT. And because there's so many variables in this equation, I like to make myself a list and pull it out of the problem to keep my numbers straight and plug them into the right places in the equation. So the pressure that we're given is 1.5 atmospheres. The volume that we're given is 8.56 liters. We are asked to find the number of moles of H2, so that's what we're trying to find there. The gas constant is 0.08206 liters times atmospheres divided by moles times Kelvin. And then the temperature that we're given is 0 degrees Celsius. So we need to add 273 to that to get our temperature in Kelvin, which is just 273 Kelvin. The other thing that I like to do before going to do my calculation is solve my equation for my unknown. It's easiest for me to solve a problem if I can see all my numbers and see my units, and I don't like rewriting the problem over and over again. So if I solve this before I plug any numbers in it for the variable I'm looking for, that saves me a little bit of time and work. So we want to get n by itself. So we need to divide by RT on both sides. We cancel out RT on the right, and so our new equation is PV divided by RT is equal to N. So the first pressure that we have is 1.5 atm. The volume is 8.56 liters. The R value is 0.08206 liters times atmospheres divided by moles times Kelvin. And the temperature is 273 Kelvin. All this is equal to the number of moles. So we need to take 1.5 times 8.56 divided by, in parentheses, 0.08206 times 273 and close the parentheses. And you should get 0.57 moles of hydrogen is equal to your N. So the reason why I knew it was moles for my unit is because you can cancel out atmospheres, liters, and Kelvin. So moles is my only unit that I have left. The second example says, suppose you have two 200 liter tanks that are to be filled separately with gases of helium and hydrogen. We want to know what mass of each gas is needed to produce a pressure of 135 atmospheres in its respective tank at 24 degrees Celsius. So I'm going to underline the numbers and units that I'm given in this problem. And then I'm going to make myself a list of the variables from the ideal gas law equation and pull the numbers out of the problem and assign them over here. So my first pressure unit is 135 atmospheres. The volume unit is 200.0 liters. We don't have it in value. The R value is still the same. And the temperature is 24 degrees Celsius, which we need to convert to Kelvin by adding 273 to it. And you should get 297 Kelvin. So in our ideal gas law equation, we have a pressure value, we have a volume, we have our R, and we have our T. So we're going to need to solve again for the number of moles. And then we are going to convert moles to grams. So we're going to find moles. And then multiply by the molar mass. To get our grams. So our pressure is 135 atmospheres. The volume is 200 liters. The R value is 0.08206 liters times atmospheres divided by moles times Kelvin times 297 Kelvin. So atmospheres are going to cancel, liters cancel, and kelvins cancel. So 135 times 200 divided by, in parentheses, 0.08206 times 297, close your parentheses, for your number of moles. Since we need 3 sig figs, you're going to get 1,110 moles. Now we need to multiply by the molar mass of our gases to get the mass of each gas. So for helium, we're going to take 1,110 moles, and the molar mass of helium is the same as the average atomic mass, which is 4 grams per mole. So 1,110 times 4 is going to give us 4,440 grams of helium. And then for hydrogen, we're going to again take the 1,110 moles, and we're going to multiply it by the molar mass for hydrogen. Now remember that hydrogen is a diatomic molecule, so it's H2, which means we need to take 2 times the average atomic mass for hydrogen, and we're going to get 2.016 grams of hydrogen. So we can cancel out our moles of hydrogen. 1,110 times 2.016 is going to give us 2,240 grams of hydrogen. So that is example B. We have one more example to take a look at. This example says a sample of diboron gas, B2H6, is a substance that bursts into flames when exposed to air. It has a pressure of 345 torr at a temperature of negative 15 degrees Celsius and a volume of 3.48 liters. If the conditions were changed, so the temperature is 36 degrees Celsius and 468 torr, what is our new volume? Okay, so again, I'm going to make myself a list of the variables, and I am going to pull those numbers out. 345 torr. And if you'll notice, we actually have 2 pressure values. So we have two different conditions here. So I'm going to call this P1. V1 is the 3.48 liters. We do not have a value for N. The R is going to be the 0.08206 liters times atmospheres per mole times Kelvin. And then the temperature is negative 15 degrees Celsius. So we need to convert our Celsius to Kelvin by adding 273, and that's going to give us 258 Kelvin. Then for our secondary conditions, make a list of those as well. Our second pressure is 468 torr. We do not have a second volume. That's what we're trying to find. We don't have a second N value. R is a constant, so it's not changing. And then our second temperature is 36 degrees Celsius. So we need to add 273 to that. And that is going to give us 309 Kelvin. Okay, so because we have 2 different sets of data, we need to put on our thinking caps a little bit with this problem. And we want to ask ourselves, what are the variables that change? Well, our pressure is changing. The volume is going to change because we're trying to find a new volume. And we don't have a value for N. R is a constant, and our temperature is also changing. So the values, or the variables that remain constant, is definitely our R value, because it's always constant. And since we are not given a value for either of our N's, we're also going to assume that our number of moles is staying constant. And if we reread the problem, it doesn't say anything about changing the amount of gas. It just talks about changing the conditions. So we're going to assume that we have this diboron gas enclosed, and then we just change the temperature, which changes the pressure on it. So we need to write the ideal gas law so the variables that change are equal to those that are held constant. So PV equals nRT. Okay, so we know that N and R are held constant. So we're going to divide by T on both sides to isolate N and R. So PV divided by T is equal to NR. And since NR is held constant in both, we can say that P1 times V1 divided by T1 is equal to NR, but that is also equal to P2 times V2 divided by T2. Or we can write this as P1 times V1 divided by T1 is equal to P2 times V2 divided by T2. Now you could plug your numbers straight into this equation, or you could go one step further and go ahead and solve it for your unknown, which is what I would like to do because I just don't like writing my numbers over and over again. So to get V2 by itself, we need to multiply by T2 over P2 on both sides. This is going to cancel out the P2 and the T2. And so our new equation is going to be P1 times V1 times T2 divided by T1 times P2. All of that is equal to our second volume, V2. So now, plugging our numbers into this equation, because we were able to get rid of our R value, we can use the torr for our pressure. So we're going to have 345 torr times our first volume, which is 3.48 liters, times our second temperature, which is 309 Kelvin, divided by the first temperature, which is 258 Kelvin, times P2, which is 468 Kelvin, all that is equal to V2. We can cancel out our Kelvin, or this is 468 torr, I'm sorry. Wrote the wrong unit. But we can still cancel out our Kelvin. And we can also cancel out the torr. So we're left with liters. So 345 times 3.48 times 309 Kelvin divided by, in parentheses, 258 times 468, and close your parentheses. Your volume should be equal to 3.07 liters for that second volume. If this last example, you need to see it some more or read over it, this example is found on page 177 in your book. Also remember that we are in chapter 5. Chapter 5.3 is the section that talks about the ideal gas law, so if you need to look over that some more, that would be a great place to take a look. Your assignment will be posted onto Canvas. Thank you. Have a great day.